Hi, welcome back. This is Ravichandran from the Mountain Path Academy. Welcome to this session number 6 to discuss stationarity for time series analysis in continuation with the ARIMA model. So, last session we discussed basics of ARIMA model, and one of the most important requirement for any time series analysis forecasting is stationarity. So, what is stationarity? We'll discuss this concept. What is stationarity? Why it is important? How to visualize time series data in Excel to look at non-stationarity and stationarity. Then testing for non-stationarity with simple means. Then testing and for a unit root, that is simple ADF test, Augmented Dickey-Fuller test using regression. Then also discuss what is differencing, how to take how to convert a non-stationary data into a stationary data after differencing. We will also use Excel to show how it can be done. At the end, we'll also automate using and Python also. We'll upload the time series data. So quickly transform the data into a stationary data by conducting test before and after differencing. So first, let's quickly understand what is stationarity. So stationarity means when the statistical property of the time series data remain the same, they remain static. That means constant mean, constant variance, and a stable autocovariance. Again, we'll discuss a little bit of autocovariance and autocorrelation next session. So that means the mean has to be more or less constant and a constant variance. It's very difficult, but even after so we will only look for a weak stationarity, not a strong stationarity for a requirement. No. So classic forecasting models like ARIMA model, ARIMA model, assume the time series is stationary. A stationary series is predictable, that means its mean variance are more or less stable. A model non-stationary data, so you don't get a proper analysis, so you get spurious trends and misleading forecasts. So we make the data stationary first and then fit the model with the confidence. So stationarity is nothing but an ARIMA model we discussed last session. So it's an integrated step. So auto regression and moving average, it is integrated through stationarity. So first, how do you look at the whether a given data is stationary or not? So we just put the data into Excel. We use a simple and plot the series and read the picture. So as soon as you see the series got an upward trend, and then we can all upward or a downward trend or a spread like a funnel, or we can always say whether that given data, given series is stationary or not. Now, so look at this picture, the diagram. You can see that the series with the linear trend. We are going to see that in Excel also. So that means clearly on the left side you can see the data is a non-stationary. It has got a clear trend. Similarly, we can also use what is called a rolling mean and a rolling standard deviation to see that the data is non-stationary. So that means we can easily look at it. Original data is so we can come to conclusion. But we are not going to stop with that. So we'll first what we'll do. So once the data is non-stationary, we'll use what is called differencing. So what is differencing? So differencing is subtracting each value from the one before the value. That means change in the differencing, change in the y is equal to yt minus 1. So what is an advantage in differencing? It removes the trend. So that means we can easily do even one differencing, d is equal to 1. That means we can remove the trend. So in ARIMA model, the d represents what is called the integration, that is removing the trend. That's very important. So if you really look at the diagram, the original first one is a raw data which has got an upward trend. Now once you differentiate, we can see that the what is called the trend is removed, then the data becomes stationary. So look at this one. After doing the difference 1, and the data, you get the trend becomes a straight line, and also you can calculate the rolling mean and standard deviation. So we can Even with one differencing, you can actually do what is called a data as a stationary data. Okay. Now, you can look at this one. This picture gives a very clear one. So, what is the original raw data which has got an up and down trend? Whereas once it after differencing, you can see the green color data, which is what is called a stationary data, a data transformed into stationary with the difference of d is equal to 1. So we are going to do in Excel first the simple mean test. What you will do, the first half of the data and we'll take the mean and the variance. Second half of the data will take the mean and the variance or standard deviation. If there is a difference between the first and second, we come to conclusion the series may not be stationary. So it's not a firm conclusion. So that is one way. So we also do the most important test, what is called the ADF test. It's called Augmented Dickey-Fuller test. So we'll assume the given stationary is non-stationary, and then the alternative hypothesis is we'll say the stationary is a station. The data is stationary. We'll just calculate the test statistics. If the test statistics is more negative than the critical value, then we'll conclude that and the data, that means we'll reject the hypothesis, then the given data is stationary. Otherwise, we'll say and the given and series is non-stationary. So you're going to calculate. What are the steps in ADF? First is a simple linear regression. We are going to use ADF test in Excel. So first we have the original data. First we calculate what is called a lagged series. Then we actually, once you have the lag series, then what we need to do is we have a difference. So we are going to follow these steps. So first that we have to have once you want to run a regression, when you have a dependent variable and independent variable. The dependent variable y is nothing but a differenced variable. So first we will take the difference series, then we will have a lag series. So lag series is what is called an independent variable, and the original difference series is a dependent variable. So then once you have the data, then we will use a regression. We want to find out the slope and standard error. We will simply run the regression y comma x true comma true, and we will get what is called the slope and the standard error. We divide the slope by the standard error. We get what is called the t statistics. So once you get the t stats, then we have to compare with the critical value. If t stat is less than the critical value, which is for 5% is minus 2.x, then we reject the hypothesis. We conclude it is stationary. If it is not less than that, we will say the given stationary is a non-stationary. So once you have the non-stationary, we know we have to take the differentiation to make it stationary. Then this is how we do it in Excel. First we have the original data. Then what you do is actually we calculate the x variable. That means we take the lag variable, lag series. Then the y variable is nothing but the difference data or so once you have run the regression, we come to conclusion whether the data is stationary or non-stationary using the t statistics, and that means as well as we have, once you calculate the t statistics with the critical value, we'll do it. Now once even if the series has become stationary, we can actually reconfirm by rerunning the ADF test. So how are you going to do? It's a little complicated. It's not required, but you can look at that. But still we can do it. So first step is to differential level. First one, YT. Second one is second data. You have what is called and lag it by one period. Then difference the series again. Then calculate what is called the regression. So here the y is nothing but your difference of the difference series, and the x is nothing but your and lag series. So that means lag differences is your x series, and that is a lag difference series. Now the y is the lagged difference of difference, that is second one. So that means it's very easy to do in Excel, but even without retesting it, you can still and look at the visualization, you can reconfirm that. So let's go into an Excel, and then we'll come back onto and we'll do that. Now look at the data. So I have taken a real-time data of a US 10-year yield for 1 year data I have taken, and I have used Python code to download the data. So as soon as you see the data, so you can see that this data has got a what is called a lot of trend. So I also taken what is called the rolling mean, 20-day rolling mean. So and I just visualize it. You can see that this particular thing has got a what is called a it's a non-stationary. So as soon as you can see the data is non-stationary visualization, I have taken differencing. So how are you going to do the differencing? So it's nothing but so we take that means today's data minus yesterday's data. So that means you do the differencing, and then you can do the what is called do the visualization. You can see that the trend has completely gone. Now the data is become more or less stationary, so we can easily. But visualization alone is we are not going to remain with that. First test we are going to do the what is called a simple and mean test. Mean test is nothing but I will take the average of the first half of the data. So in Excel, how do you do it? You take the average, you take and the range and of the first half of the data. So I have 252 data, rows of data. So I'm taking actually 252 divided by 2. I'm taking the first half of the mean of the first half, mean of the second half. You can see that there is a difference between, there is a difference. So we can simply conclude it is non-stationary. Similarly, we can take the volatility of the first half and the second half. So we can see that difference is and 1.95%. So we can roughly conclude. We cannot be very certain, but with just looking at the mean and the visualization. So we'll go into simple ADF test, argument. So what are the first? So this is the original data is there, the time series times index and times. First step is to calculate actually, take the what is called the lag of the, so you take the lag, that means one step downwards. That means you use and one step downwards, take the lag. Second is find out the difference. So this is called the first difference. So this becomes your y variable and this lag becomes your x variable. Now we calculate what is called the ADF t statistics. So in Excel is very simple to run a regression. So we can use a Linus test and calculate that means y comma then y comma x. So that will give you what is called and comma true comma true, and that will give you what is called and. So you can see that so this will give you the slope, this will give you the slope, and this will give you the standard error. So now you divide the slope by the standard error, and we will give you what is called the t statistics. So we got the ADF t statistics, that is minus 1.86. So we have the 5% critical value, so which is minus 2.88. Now what is the main test? Whether this is less than the t statistic, the critical value. T statistic is less than. Now it is so we can always whether that is less than that one. So now we can say it is false. That means the stationary, the data is non-stationary. So that means this has to be, if it is less than this one, that means it is so given data is false, that means it is non-stationary. So that is so you can put an if condition saying that we can do always like that. So now the next step is this is the first, we have done 3 tests. One is visualization, second is we looked into the mean, and then we looked into the ADF test. Now we will do the differencing part. So now again, let's say that I have done the difference now of the original data. So I just look at the visualization, I can conclude the data is stationary, but I don't want to stop with that. I want to reconfirm using the ADF test by actually and proving that my difference data is stationary. So what I need to do is I have to take the lag of the difference here, original series. Similarly, again I have to take the differencing of the original and that is a differenced series. So this is what I do. So first I will calculate the difference. That is my action. This is the data I'm going to use, the difference data going forward. The next step is calculate the lag, then calculate the and lag of the difference series. Now this has become my y variable and this becomes my x variable. Now again use what is called calculate the t statistics. We calculate Linus function and we can true comma true. So again what we can do is divide this is your slope and this is your standard error, And we can also calculate like this: Linus and index Linus, that is y comma x, true comma true, 1 comma 1, and then you can put 2 comma 1. Then once you have calculated the ADFT statistics, then we have to compare whether this is a, so now we can easily say this one is a, so this is it less than this one, and that means if it less than this one, if it is true, then we can say it is a stationary. So now after differencing one, so we are able to conclude the data is not only visually set but using the ADF also. Now, so now we have through Excel simple 3 tests. We can also use what is called automate the whole process into Python. So what I have done is using the Python, and that is a code, I have generated what is called and US treasury data using the data. Now using the data, I'm running a code. I will upload the data. So I'm upload the data of US treasury in Excel data. Then this code will automatically run, and whether the data is non-stationary. If it is non-stationary, and then I'm going to upload the US treasury yield data, treasury data. I have uploaded it now. Then now automatically it will say that now it uploaded the data. Original data is, you can see it is an upward trend, is non-stationary with a rolling mean. It is also conforming with the auto correlation, saying that it is a slow decay non-stationary, which we'll discuss next session. Now look at this one. After differencing, the given time series data has become, trend is completely straight line now. So it has become a stationary data. We can also look at the rolling mean and standard deviation, which is also more or less straight. Now we can see that autocorrelation also, there is a slow decay conforming the, and that is so that means after differencing the data, that means this has become actually a stationary data. Now look at the diagram here, and this is before the differencing, this is after differencing, which is very clearly proving that after one differencing, the data has become stationary. So we can also conclude joint verdict using the ADF and KPSS test. KPSS is little complicated to run through Excel, but now it is very clearly using ADF test. You can see that and it is less than the critical value. That means it is stationary. Similarly, in KPSS test, it is greater than the critical value, again the stationary. So that means through visualization, through and what is called all other means, actually we also taken what is called and we have used what is called all the methods, clearly prove that the data, original data which was non-stationary, after differencing one, it has become stationary. So now let's conclude. So that means and differencing the data, you can actually make the data stationary, which will be the data will be fit to and proceed with the ARIMA modeling. That is one of the requirement. So you have done the automation part. So what are the key takeaway from this? Number one, what is stationary, which has got a constant mean variance? Then just look at the graph itself. So we can look at the Excel graph, we can visualize it, and then we can quickly check and using the mean, and then we can use the ADF test. We can reconfirm it. We can also automate using Python also. So next session, we will actually discuss about what is autocorrelation, what is partial autocorrelation. So thank you for watching. Thank you.